Hello guys, this is Sky Academy. Today we are going to look upon the electron configuration of atoms and the ions. Yes. So simply before looking upon the electron configuration, simply electron configuration, this is how electrons are distributed in their respective orbitals. In previous sessions, we have seen about the atom, the protons, the electrons, and neutrons, and the discoveries of those subatomic particles. Then today we will look upon how electrons are distributed in their respective orbitals. Yes, but before going there, we need to look upon some laws which govern the distribution of electrons. Yes, the electron configuration, this is the distribution of electrons of an atom in its atomic orbitals. Then there are three laws which govern how electrons are distributed. Those laws, we have what we call Aufbau principle. Yes, we have Aufbau principle. We have Pauli exclusion principle and the Hand's rule. Yes, we have Aufbau, Pauli, and Hand. So those people have told us how we can distribute electrons, yes, in their orbitals, so that they fulfill the stability. They cannot, yes, they follow all the rules. So here, by Aufbau principle, simply Aufbau principle states that atomic orbitals of lower energy must be filled before the higher energy orbitals. Atomic orbitals of lower energy must be filled before the higher energy orbitals. To understand this, this is the law of breathing up. Principle, this is the principle of breathing up. According to that principle, if an atom has only one electron, this electron will occupy the lowest principal quantum energy level. I think you need to know also the quantum numbers. When we say principal quantum number, it is equal to, we say n when we have one electron, means n equal 1. So we have the lowest energy level. Yes, we start with the n equal 1. That is the lowest energy orbit. So by this law, if an atom has only one electron, this electron will occupy the lowest principal quantum energy level. And the lowest energy orbital in that principal quantum energy, simply we have also when you have one, this is equal to 0 and equal to s. To understand the principle, sorry, this is the orbital s. When we say orbital s, we come back to the quantum numbers. The quantum numbers says that when you have the principal quantum number n equal 1, then the secondary quantum number or azimuthal quantum number is we take n minus 1. N minus 1. So if you have 1, means that n minus 1 is equal to 0. And then this also correspond 0 correspond to s orbital. S orbital. 0 correspond to s orbital, 1 correspond to p orbital, 2 correspond to d orbital, and 3 correspond to f orbital. I think those quantum numbers, you know them, so we may not spend much time on this. Maybe if you don't know it, you write it in a comment so that you can look upon the quantum numbers. But for now, we say that if you have one, the principal quantum number which is equal 1, then to look upon the secondary quantum number, we say n minus 1, and then it becomes 0, and the 0 corresponds to SC orbital. So, by representation, when you have one electron, this is represented as 1, of course, 1 which is represented as the principal quantum number, and the S which represents the orbital, and then this one also corresponded to one electron, meaning that one electron in S orbital of the first energy level. That is 1s1. When you say 1s1, the meaning we have one electron in S orbital of the first energy level. Okay. If the atom has 2 electrons, the second electron will be filled in the same s orbital to give the structure 1s2. Also, if you have 2 electrons, the second electron will be filled in the same s orbital to give the structure 1s2. Means that you have 2 electrons which is in s orbital, also s orbital found in the first energy level. So, Alphabet principle, what he was trying to say, atomic orbitals of lower energy must be filled before the higher energy orbitals. It means that this, if we have one, it is the first energy level. So, if it is the first energy level, must be filled before higher energy orbitals. When we come to 2, we can also look upon 2. We have 1s, 2s, 2p. You cannot go to 2s, you cannot fill the electrons of 2s before filling the electrons of 1s. Also, in an orbital, you need to have 2 electrons. You cannot fill more than 2 electrons in s orbital. The maximum number of electrons which can be accommodated by s orbital is 2. The maximum number which can be accommodated in p orbital is 6. The maximum number which can be filled in d orbital is 10. The maximum number which can be filled in f orbital is 14. That is the law. That is how it is done. So, if after filling 2 electrons in S, then, for example, if we have an atom with 3 electrons, then the third electron will be filled in the second energy level. We have first 1s, we have 2s, so 2s also will accommodate one remaining electron, and then you have 3 electrons. So we will get understanding as we proceed the lesson. Then note the way of notation. The first number indicated the principal energy level or principal quantum number, followed by the letter indicating the orbital, followed by the number of electrons present in the orbital as superscripted. This is explaining how we feel this notation. This notation shows this. We said that this is the principal quantum number, 1 representing principal quantum number, S representing the orbital, and then this 2, which is superscript, is the electrons. That's what have been explained here. Then we can jump to Pauli exclusion principle. Pauli exclusion principle. The first one, we said that atomic orbitals of low energy must be filled before the higher energy orbital. That's the simple as that. Atomic orbitals of low energy must be filled before the higher energy orbitals. Only that. And then the second law says that Pauli exclusion principle says that, or states that, in an atom, 2 electrons cannot have 4 quantum numbers identical. I think you will understand this. In an atom, two electrons cannot have four quantum numbers identical. What does it mean by four quantum numbers identical? Uh, Let us use this figure here. You see, this figure contains two electrons. Two electrons, and but the notation of electrons, they are spinning. They are spin. We represent using spin. This is spinning up, and this is spinning down. Uh, then this notation shows that we have two electrons in this figure, but those two electrons have different direction. One is spinning up and another is spinning down. What does it mean? Then we said that in an atom, two electrons cannot have four quantum numbers identical. In fact, what they want to mean here, you cannot have two electrons which are spinning in the same direction. You cannot have two electrons which are spinning in the same direction. For example, but before going to an example, here there is another thing. To understand this Pauli exclusion principle, this explains why two electrons in the same orbital must have their spin opposite. Yes, if you have two electrons in the same orbital, they have to spin in different direction, in opposite direction. Like this one up and another one is down. So it means that they need to spin in different direction, in the opposite direction as you see here. So let us look upon a scenario where we have what is different in this. For example, Pauli exclusion principle doesn't allow us to put a third electron in the same orbital. Since if we put the third electron in the same orbital, two electrons will have four identical quantum numbers, and this is not allowed. This is not allowed. This is the scenario I was telling you. You see here, we have the first electron which is spinning up, the second electron which is spinning down, and the third electron which is spinning up. In fact, we have the first electron which is spinning up, and the third electron which is also spinning up. This is not allowed because we have two electrons which are spinning up, and it is not correct. Why it is not correct? Why we cannot put electrons as we have them? Earlier in this session, I was telling you, I have told you that we have a maximum of two electrons in orbital. You cannot have more than two electrons in an orbital. The maximum number of electrons in an orbital is 2. In other words, the Pauli exclusion principle is telling us that you cannot put more than 2 electrons in an orbital. The maximum number of electrons in an orbital is 2. So, if the maximum number of electrons in an orbital is 2, means that even those 2 electrons, they needed to have to be spinning in opposite direction. One is spinning up and another spinning down. To avoid the coincidence or how Simply, an electron is determined by the quantum numbers. When we say electron, simply to know the location of electron, to know the direction of electron, everything you wanted to know about electron is determined by quantum numbers. Because we have two theories. We have two theories which explain about electrons in their orbitals. The first is Bohr's atomic model, and also we have another model of Schrödinger. The Bohr's atomic model we had I can say, different limitations. Bohr had a different limitation. That's why Schrödinger um, came up with his quantum numbers, and then those quantum numbers are able to show electrons in their orbitals. It is able to show. It's able to show the direction of electron, the position of electron, yes, the probability of finding electron in the orbitals, the position, the direction, and so forth. So those are four quantum numbers. We have seen that the first quantum number is the first quantum number or principal quantum number is the one which show, yes, which show the energy level, which show the energy level. And the secondary quantum number, we have seen that for this example, we have seen that, for example, if we have a principal quantum number, yes, then the result, the secondary, they show orbital, and then the third, they show you, I don't remember quickly, but those quantum numbers try to show us where electron is located. For example, the spin quantum number show if the electron is spinning up or spinning down. Spin quantum number show two opposite direction, if it is up or down, if it is +1/2 or -1/2. If it is +1/2 means it is spinning up. If it is -1/2, it means it is spinning down. So this law says that you cannot have four quantum number identical. Means that if one quantum number is showing about the electron which is spinning up, another four quantum number need to express the electron which is spinning down, but you cannot have another electron which is being explained by the four quantum numbers as the first one. This is not correct. That's why the law says in an atom, two electrons cannot have four quantum numbers identical. I think we have used the much energy to explain this law, this principle. So I think you understand this. If you don't understand it, you may write it in comment. I may explain it to you so deeper by using those quantum numbers. But I think this law is understandable. Only it is showing that you cannot have two electrons which have the same spin. That's it. In an orbital, you cannot have two electrons which have the same spin, which is spinning in the same direction. Only one needed to be up, which one needed to be spinning up, and another needed to be spinning down. So we don't have another third electron, and that's a principle. You need to take it as it is, but as long as there are explanations, you can get it. So there is another rule which is called the Hand's rule. Hand's rule states that orbitals of equal energy are each occupied by one electron before electrons begin to pair up into the same orbital. Then let me repeat again once. Hand's rule stated that orbitals of equal energy are each occupied by one electron before electrons begin to pair up into the same orbital. For the first row, we have seen that if for the first row, this alphabet principle we're looking at, if you have one electron can be put in s orbital, and then if you have two electrons also you can put it in s orbital, and then it's correct. Now we are looking upon the orbitals which have the same energy. For example, atom with the 6 electrons are filled like this. When you have atom with the 6 electrons, for example, you have one s, and then you put 2 electrons, as the row says, 2s, you put also 2 electrons, s orbital, we have said s orbital accommodate maximum of 2 electrons. Then if you come to 2p, we will count. We have 2 for s, 2 for s, therefore, and then we remain with the two electrons remaining are going to be put in p orbital. That's no problem. But for s, no problem. For 1s, no problem. For 2s, no problem. But when you come to 2p, there's a problem. Because the p orbital also has 3, we have 3p orbitals. We have 3p orbitals. We have px, py, and pz. I think in earlier lessons we have seen about the orbitals and how their shapes. Yes, the s orbital, how it is circular, and the p, we have seen px, py, and pz, so no problem. When it comes to px, py, and pz, some may say that we have px which can accommodate 2. So they can think you can put px with the 2 electrons as we have, and then it is finished. But not the case. We said that when you have orbitals have the equal energy, means there's a p have the same energy. We have px, py, and pz, or those p have the same energy. So if they have the same energy, means we have to fill with 1 electron, 1, 1, 1 if they are available, and then after filling 1 electron, we then begin to pair. We then begin to pair. For example, if you have an atom with 10 electrons, you can add 2, 2, and then, for example, 8 electrons. 2, 2, and then you remain with 4 electrons. For 4 electrons, first you add 1 in px, another one in py, and another one in pz, and then you remain with 1 electron. So the another electron is going to be paired in px. So we feel like that. I think you understand. Put 1, 1 because there are 2. If there are 3, you put 1, 1, and 1. If there are 4, we put 1, 1, 1, 1 here in px. If there are 5, 1, 1, 1, and then you begin to pair up into another, and then they are filled. When there are 6, no problem. You put 1, 1, 1. There are 3, and then you begin with the remaining 3. Pair up px. You pair up in py, and you pair up in pz. So this is because we have 3 p orbitals with equal energy, px and py and pz. They have the same energy. So you have to occupy. You have to fill 1 electron in each p, and then you begin to pair up in the same orbit. So that is the Hand's rule. I think also it is understandable. When building the electron configuration of elements, you must be guided by the principles and rules seen above. Yes. When building the electron configuration of element, you must be guided by the principles and rules seen above. So you need to respect these rules in assigning electrons in their respective orbitals. So writing the principal quantum number first, followed by the orbitals, immediately followed by the number of electrons in the orbital as superscript. Yes. You need to follow also this. You have to write first the principal quantum number, which is followed by orbitals, and then followed by the number of electrons in the orbitals as a superscript. So a useful and simple aid for keeping track of the order in which electrons are first filled for each atomic orbital. The different orbitals are filled in the order. So you have seen me, I was telling you that 1s, 2s, 2p. You may ask yourself, which order we follow? The order we follow is this one. We have 1s. We have 1s. We say 1s because 1 it is principal quantum number, s is orbital. You may ask yourself how many electrons are going to be accommodated in s. Electrons, maximum electron accommodated by s, I have said it is 2. So anywhere you find the s, you know the maximum electron is 2. The maximum. When you say maximum, we have also the minimum. We have also the minimum, maximum. So if it is maximum, there are 2. But if it is not maximum, you may find 1 electron here. For the case of hydrogen, 2s also maximum is 2. Anywhere you find the s, it is 2 electron maximum. Anywhere you find the p, it is 6 electron maximum. Anywhere you find the d, it is 10 electron maximum. Anywhere you find the f electron, it is 14 electrons maximum. So 1s, so we are going to, so we cannot put electrons here because we know the way we can use in order to know electrons. Simply, when we say atomic number also tells you the number of electrons. Simply, atomic number shows the number of electrons. You have seen that the number of electrons are equal to the number of protons are equal to the atomic number when it is in a neutral atom. So we have seen it. So if atomic number is 10, also electrons is 10 for a neutral atom. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. This is the order we need to follow. Means that for the case when an atom have for example 35 electrons. So we put here 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. When we reach 2, 3d, we need to know if 35 have not filled. 2 here maximum, 2, 10, sorry, 2, 4, p6, 10, 12, 18, 20, 30, 4p. 4p will accommodate 5 electrons in order to have 35. So we will close here for an atom with 35 electron because we have seen that 35 will close here, but because it is 5, this P accommodate a maximum of 6 electrons, but because it is 35, 30 is here, then we need to put 5 here. I think you get understand. So you will ask yourself where this order came from. I will explain it later. Notice that as energy levels increase, starting from n which is equal to 3, 4s orbital is filled before 3d, 5s before 4d, etc. But when ionized, 4s electrons are ionized before 3d and 5s before 4d. This order has what I can call exception. You see, when you come to n which is equal to 3, n which is equal to 3, we have 3s, 3p, then we go to 4s. Go to 4s before 3d. You may ask yourself, oh, why we put the 4s before 3d? That is the order. That is the order. Have you seen 4s is written before 3d and no problems there. 5s here is written before 40 and no problem. And so forth. So those are not problems. There are exceptions, but there is no problem in it. So you follow this order as it is written. So in filling electrons in their respective orbitals, we use this order. But when we come to ionizing, when ionizing, for example, when an atom loses electron, it do not follow this order. When ionized, 4s electrons are ionized before 3d. For example, we have 4s 3d. For example, atom will finish here. Its orbitals ended here. We have 4s and 3d. You may ask yourself, we may say I'm going to remove the electrons of d before 4s, but in ionizing, we remove electrons from 4s. Then after being removed, you can then come to 3d. That is the two exceptions you have seen here. So if you have a question, you may ask in the comment so that we may clarify. We may clarify in the other lessons. Yes, we may plan for another lesson, but those questions realized may be asked, so we may start from there. So I have told you that I will show you where the order came from. This order came from here. When you are writing your orbitals, you write 1s, 2s, 3s, 4s, 5s, 6s, 7s. You stop with the 7 because we have not already discovered any atom which have more than this graph written here. By stopping with the 7s, all atoms jump in this graph, so we cannot continue with the 8s, 9s because those atoms have not already discovered. We have seen that we have 118 atoms which have been elements which have been discovered. So they fall in this graph. Then we say 1, 2, 3, 4, 5, 6, 7, and then you put S. Then when you come here, we start with the 2. 2, 3, 4, 5, 6, 7. We stop here. Then we add the P. Then we start with the 3, 3, 4, 5, 6. You can even write 7 here, yes, and then we add D. Then when we come to F, we go to 4. 4, 5, 6, 7. No problem if we reach to 7, but they have reached 5, no problem. Then you add FF. Then you trace a horizontal, sorry, an oblique lines there, like this, there, and then you see. And then when you count, you come here, you put a flash here, and then this is going to come, yes, back here, like this, back here, back here, like this, like this, like this, like this. You see my cursor where it moves. Come here like this, like this, like this, like this, and this, and this. Yes. So means this is 1S, then 2S as you see. You come here, 2P here, 3AC, 3P, 4AC, 3D, 4P, 5AC, 4D, 5P, 6AC, 4F, 5D, 6P, 7AC, 5F, 6D, 7P. That is the order you have seen this one. Okay? I think we can now jump clearly to electron configuration with the different atoms. In assigning electrons in the respective orbitals, you have 3 ways. There is what we call expanded notation, orbital box representation, and noble gaze notation. So for expanded notation, it is looked like this, the one we are familiar with. For expanded notation, we have this one is hydrogen, has atomic number of 1, so we say 1s1. 1s1, this one you have seen that is an electron, number of electron. By this order, we are not going to suffer too much because we have seen the order we follow. If it is hydrogen, it is 1s, then you put 1 electron because atomic number is 1. If it is helium, we put 1s, then you put 2 because it has 2 electrons. So then we jump to another orbital because we have seen that the maximum number of electrons commutated by s orbital is 2. So 2 for in helium. So if you have lithium, which have 3 electrons, we jump to another 2s, then you put 1. I have 2 here and 1 here, then there are 3. Then, for example, if you have carbon, also we follow the order. So helium 2 electron, 2s2. But here there is a mistake. Cannot jump to 2. Here it is 1. So this is a mistake. Here we put 1s2. 1s2. Here we have 1s1 because it is 1 electron. Here we need to put 1s2. So I'm sorry for this mistake. Then we have lithium. It has 3 electrons. It is 1s2. Then if it is 3, another electron needs to put in another energy level, so 2s1. 1. Beryllium with beryllium with 4 electrons with atomic number of 4. It is 1s2, 2s2 because it is 4. Maximum. Boron, which has atomic number of 5 electrons. 1s2, 2s2, 2p, 1. 2, 2, 1, it is 5. I think you see here. Then carbon atomic number of 6. 1s2, 2s2, 2p2. 2, 2, 2, it is 6. I think you follow the order. Neon, which have atomic number of 10, it is 1s2, 2s2, 2p6. You can even continue with the, for example, if you have aluminium, you can add aluminium which has atomic number of 13. You can do one S2, 2S2, 2P6, 2P6. It is then 3S2, 3P1. But this aluminium is a 3 plus. If it is a 3 plus, aluminium has been ionized. When it is ionized, it is going to be when it is ionized, electrons are going to be are going to be affected. Electrons are going to be affected. So if it is ionized, it has a 3 plus, means the aluminium has lost 3 electrons, means that aluminium 13, we normally know that its atomic number is 13, but because it has lost 3 electrons, it will remain with 10. It will be isoelectronic with neon. The electron configuration of aluminum 3 plus resembles to the one with the neon. So we say that neon and aluminum 3 plus are isoelectronic. Isoelectronic means they have the same electronic configuration. Then we come to this sulfur 2 negative. Sulfur 2 negative. In fact, this is sulfur 2 negative. Sulfur normally sulfur has atomic number of 16. Of 14. After gaining 2 electrons, we say 2 negative. When you say 2 negative, means that the sulfur has gained 2 electrons. You know, losing and gaining, that's it in chemical bonds. In chemical bonds, metals lose electrons and metals gain electrons. So this sulfur is non-metal, so it has gained 2 electrons. So its its electrons have added with the 2 value. So it has atomic number of 16. So we have 1s2, 2s2, 2p6, 3s2, 3p6. We have 2, then 2, 10, 18. Sorry. Sulfur has the atomic number of 16. After gaining 2 electrons, it has got 18. That's why it will have 2, 10, 2, 6, become 8. 18. This one has electronic configuration resembling to the one of argon. The one of argon. Yes, we know that when an atom gain or lose, it gain or lose in order to resemble to the one of noble, the electron configuration which resemble to the one of noble gases, because noble gases are stable, they do not need to make a chemical reaction. So that's it. Here we need to put 18 here, not 16. Okay? I think this expanded notation, you know it. You understand it. So there is another notation which is called the orbital box representation. For the orbital box representation, also we need to put the electrons in the orbitals in this way, in box like this. For example, if you have hydrogen we have seen it is 1s1. So in the box we put one electron because it is the one accommodated by hydrogen. So when we come to helium it is 1s2, so we put two electrons. Those two electrons need to be put in according to the laws. One needed to spin up and another needed to spin down. That is no problem. When we come to lithium it has 3 electrons, so it is 1s2, 2s1. So you need to put 1s2, 2s1. For 1s2, there's a two electron needs to spin in positive direction, but another one needs to be spinning up. When it is one electron needs to be spinning up, and when it is another electron needs spinning down. So no problem with this. Beryllium with the 4 electrons, it will have 1s2, 2s2. Both spinning, one is spinning up and down, up and down. No problem. They need to be put in a box. Maybe those boxes which are empty do not need to be put here, so you need to follow this one. Only you need to write this one, box 1 and box 2, because they have four electrons. Boron have 5 electrons, so it is 1s2, 2s2, 2p1. So they need to be spinning like that. I think there's no problem. And then a carbon with the 6 electrons, you need to have a box with the 1s2, another box with the 2s2, another box with the 2p2. You see, those two electrons have been spinning up, both in different orbitals. You see, this law have said by Pauli. Pauli exclusion principle said that, no, is this Pauli? Not, I think it is Hand. Hand said that the orbital with equal energy, if you have orbitals with equal energy, the electrons must be filled in the respective and each orbitals, and then you begin to pair up in the same orbital. Means that here we cannot put these two electrons in these 2px. You need to put one electron in 2px and another electron in 2py, because we have the 2 electrons. That is enough. But you cannot put those 2 here or here or here. One here and another here. If there are others, you add another here, and then if it is to pairing, you pairing here like this. It needs to follow the order. So I think there is no problem. Then when you come to nitrogen, have 7 electrons. You have, this is 1s2, 2s2, 2p3. So as you see, those 3 electrons, because those orbitals px, py, and pz have the same energy, you need to put 1, 1, and 1. So no problem. Neon with the 10 electrons. So we put 1s2, 2s2, 2p6. Yes, because it is 6 electron, 1 here, 1 here, 1 here, and then you begin to pairing, and then you get 2p6 fulfilled, because you have 6 electrons, maximum of 6 electrons accommodated by p orbital. Then sodium with 11 electrons, you put 1s2, 2s2, 2p6, then 3s1. I think orbital box have been understood. Then let us jump to noble gas notation. For the noble gas, There is another thing you need to know for the noble gaze. When using this method, the following steps are respected. First step, you identify the noble gaze whose electron configuration is included in that of concerned element. In order to fulfill the noble gaze notation, you identify the noble gaze whose electron configuration is included in that of the concerned element. For example, if I'm looking for if I'm doing the electron configuration of carbon, the concerned noble gaze is helium. Yes, it is helium because carbon has 6 electrons, so only the noble gaze concerned is helium. But if I'm doing, for example, the electron configuration of sodium, the concerned noble gas is neon because neon has 10 electrons and sodium has 11 electrons. Means that sodium neon far in sodium. So the second, you write the chemical symbol of the identified noble gas within the square bracket. You call this noble gas core. Here, you are going to then to identify the noble gas. Write the chemical symbol of the noble gas. Chemical symbol in the bracket, so no problem. You write it. Then you add electrons beyond the noble gas core. Then you write the. So let us check it here. Because the third step it is to add those electrons which are remaining. For I have said, for example, for the sodium, I have said that if I use neon, neon is covering those orbitals. The first orbital, the second, the third. 1s2, 2s2, 2p6 means that neon covers these 10 electrons. So I put neon like this, and then I put in bracket, and then I'm going to add the electrons remaining on sodium like this. That is the noble gas notation. For those atoms or elements which fall in argon, argon means argon has 18 electrons, means that those atoms which have more than 18 electrons but below 28, yes, below 28, they need to fall in this argon. For example, magnesium has but magnesium is still using neon because magnesium has 12 electrons, means that only we have this part which is core and then 3s2. Those are the remaining electrons. In fact, to write the noble gas notation, first of all we needed to know the expanded notation. If you don't know expanded notation, how can you know noble gas notation? It might be hard for you. Simply, you need to write the expanded notation, and then you find the noble gas which fall in that electron configuration, and then you put in core, you put it in bracket, and then you write the remaining electrons like this. 2 plus 6 it is 10 electrons, it is neon, and then you write neon, and then the remaining electrons are 3s2. For calcium, because it is 20, means it is going to the argon is going to fall in calcium like this. Argon is going to fall in calcium, so here argon is going to be put in bracket with the 18 electrons. You count 2, 4, 10, 12, 18, and then the remaining electrons are those in 4s orbital, 4s2. You put 4s2. This is the notation, the noble gas notation. attention. Then we jump to we are coming to chromium. For the chromium, we have 1s2, 2s2, it is 24, 1s2, 2s2, 2 pieces, the 3s2, 3 pieces, 4s2, 3d, 4. But in order to put, there is another thing I'm going to add. When you write this chromium, it has 24 electrons. 24 electrons. So you may write like this: 1s2, 2s2, 2 pieces, 3s2, 3 pieces, 4s2, 3d, 4. But here you may write like 3d, 4, 4s2, or 4s2, 3d, 4. But 4s2, 3d, 4, this atom is unstable. This atom is unstable. We have two ways of stability when writing this electron configuration. Maybe this reason there is a part which is in senior 6. Which deal with the transition metals. For the transition metals, you to have a d orbital which is stable, it needs to be fulfilled with 10 electrons or half filled with 5 electrons. So, any other way which can be done in order to make a d orbital stable, it can be made. So I can withdraw 1 electron from S because of S was accommodating 2 electrons, and then I put it to D. As long as I see that it is going to attain stability. So I withdraw 1 electron from S, remain with 1, and then D for 5. Then the stability is this one. After gaining stability, then I check the the atomic number which have 18. For argon, I take 2, 4, 10, 12, 18. It stops here. This part is the argon. Then I write argon in bracket. Then I add those 4s2 remaining 5. 4s2, 3d, 5. This atom is stable. So in fact, I did 2 things here. First of all, I made the atom stable, and then I put argon, then to become. I write a noble gas notation like this. Okay. I think this is enough for the noble gas. Maybe the meaning is reserved for those who has questions. So here there are some exercises. Here you are asked to bullet the electron configuration of the following atoms: hydrogen, lithium, boron, sodium, argon, potassium, scandium, chromium, iron, and copper. Then the second question: write the electron configuration for each of the following pairs of ions. State the most stable ion in gaseous state and explain your choice. For the question 1, it is understandable. It is to write electron configuration, no problem. You follow those rules you have seen. But also you need to know if an atom needs to be stable. If you can do it, you can do it. If you can withdraw electrons from S orbital and then you fulfill it to D orbital, you can do it so you attain your stability. That is the Q. But for here, it is to write electron configuration. You write electron configuration of kappa plus and the kappa 2 plus. After writing the electron configuration, you compare the one which is the most stable, and then you explain your choice. If you say the kappa plus is stable, is more stable than kappa 2 plus, why? Then what you did here, you do it also here on iron. Iron 2 plus and iron 3 plus. Simply for hydrogen, I think it is 1s1, no problem. For lithium, it is 1s1, 1s1, 1s2, 2s1. Okay. Okay. For boron, but those we have seen them. For boron, it is 1s2, 2s2, 2p1. Sodium, it has 11 electrons. So it is 1s1, 2s1, 2. So 1s2, 2s2, 2p6, 3s1. For agony, but we can even we can. So this is an exercise. You can take your draft. You can take your draft. You can take the draft paper and then you take a pen and then you write your electron configuration. So you check if they are correct. Okay. So let's try to look upon their answers. For hydrogen, it is 1s1, it's correct. Lithium, 1s2, 2s1. Boron, 1s2, 2s2, 2p1. Sodium, 1s2, 2s2, 2p6, 3s1. Argon with 18 electrons, 1s2, 2s2, 2p6, 3s2, 3p6. Potassium with 19 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Scandium 21, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Chromium 24, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. For here, as you see, because chromium has 24, in fact, d orbital should have 4 electrons. But because we need to make this stable, we withdraw 1 electron from s orbital and then we put it in d orbital. For d orbital, it was having 4 electrons, but it will have 5 electrons, and then s orbital will remain with the 1 electron. This is stable because d orbital is half filled. When we have said that an atom, a transition metal, gain its stability when its d orbital is half filled with 5 electrons or full filled with 10 electrons. So this is stable because it has half of its electrons, it have half 5 electrons, but the orbital is said the orbital is supposed to have maximum of 10 electrons, but it has 5 electrons also. It is stable. So iron 26, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. This one, there is nothing we can change because even if we can withdraw 1 electron from S and we put in D, also D will have 7 electrons and in fact it will still have partially unfulfilled electrons. So it will not have gain stability. That's why we remain with it. We let it stay as it is. Then we have a kappa 29. Kappa 29, this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Also, for kappa, you see it has 9 electrons on outermost shell, means that it would have 9 electrons on D subshell of the orbital. Uh, and then, but we can withdraw one electron from S and then we put on D, which is 9, then it becomes 10, and then it becomes stable. Means it has attained this stability by simply gaining one electron from S, and there is no problem it goes to S, because even S electron also cannot move anywhere because one electron is spinning up, and then it cannot jump to another place, because another place, the electron which is supposed to be filled there needs to be spinning down, and then you have one which is spinning up, it cannot replace the one which is spinning down. So those are the answers for the question number 1. Then the question number 2, it is to make electron configuration and then comparison. So simply we are making electron configuration of ions. If it is kappa plus Z29, it will have 3p6, 3d10, kappa plus 3p6, 3d10, kappa 2 plus 3p6, 3d9. Simply you see that for kappa plus is the one which is more stable. Kappa plus is more stable than kappa 2 plus, since kappa plus has a totally filled 3D orbital, whereas kappa 2 plus have neither fulfilled nor half filled 3D orbital. This is fulfilled, that is one more stable. And then for iron 2 plus, it has a 3D6, then iron 3 plus has a 3D5. The one which have 3D5 is more stable than iron, than the one with the 3D6. As you see, it is half filled. It is half filled, and which is stable. So I think the lesson of today was somehow breathtaking, but we come to an end. Maybe you may ask some questions for clarification, but the session of today have ended. So we needed to thank you for great attention. I need everyone to take attention for this lesson, because each understanding each step as it is, the questions about the electron configuration will be, you will take every marks related to, you will earn every marks related to electron configuration, because there is nothing more they can give you other than what you have gained here. So thank you for attention. We shall meet in the next session. Okay.